So today's lesson is on power in an electric circuit. And I have equations for you here, but I'm going to show you where that comes from. Now, power is the rate at which energy is transferred. We've learned that equation before. Power equals change in energy over time. Or you can think of it as work over time as well, because work is change in energy. But we've also learned that potential difference is the amount of energy a single charge would have. So it's change in energy per unit charge. Now, if I rearrange for energy, I can get potential difference times charge, and I can put that into our power equation. So instead of energy, I will write potential difference times charge all over time. But if you look right here, charge over time, that's the definition for current. Current is the amount of charge that passes some cross-sectional area in time t. So I can replace this with current, and we get power equals potential difference or voltage times current. So this is how we can calculate power in an electrical circuit. We just take voltage and times it by current. The units are still the same. The unit of power, remember, is the watts. And it's given the symbol W. Okay. Now we can also look at a couple different ways of calculating power, because we can use Ohm's law. So if you remember Ohm's law, you got delta V, or voltage, equals current times resistance. So if I were to replace this delta V with current times resistance, what I get then is P equals I squared R. There's another way to calculate power. All right, so we have one way, two way, but I didn't have to substitute voltage into this equation. I could have rearranged Ohm's law and written it as current equals voltage divided by resistance. And then I could have substituted that into our power equation. And if I do that, you get power equals potential difference squared over resistance. So there's a third way to calculate power. And I have all three equations over here under our new equations tab. So we're going to try our first example problem. This says determine the power consumed by this light bulb in the circuit. So this is a very simple circuit. We have a voltage at our power source of 120 volts, and we have one light bulb with a resistance of 240 ohms. So we don't know current. That means if we want to figure out power, we want to use the equation that has voltage and resistance, right? Which was voltage squared divided by resistance. Okay, so if I use this, we have voltage is 120 volts, and we're just going to square that. And divide it by resistance, which is 240 ohms. And we get 60, and remember the units, 60 watts. There's the units of power. So before moving on to our second question, let's talk about some of the circuits in our house. So household safety. So you learned in grade 9 that all the wiring in your house is parallel circuits. This is important because if they were a series circuit, all someone would have to do is shut one thing off and everything in your house would go off. That'd be inconvenient. So they're obviously parallel circuits. But parallel circuit does pose a problem, as I showed you in a previous lesson when we talked about current in parallel circuits. The more things you hook up in parallel, the more current is being drawn from the power source. And that can cause a fire hazard. Right? More current, more resistance, more heat, eventually fire hazard. So we have things like fuses or circuit breakers in your house. And they are set, most households are set for those fuses to go off if you exceed 15 amps. Now if a fuse goes off, you have to actually replace the fuse, right? Because the fuse actually burns through a wire, which then opens the circuit. Whereas a circuit breaker just opens the circuit and then you push it and it closes again. I think most houses nowadays have circuit breakers. So 15 amps is the magic number here. So let's look at this second example problem. In this second example problem, here we have a circuit. It's a simple parallel circuit where we have a hairdryer which consumes 1200 watts. And that's what you'll usually see when you look at, say, an appliance or something like that, even a light bulb. It's not going to tell you current, right? Because it can't tell you current, because the current it draws will depend on how many things you have plugged in, right? But it can tell you how much power it uses in order to run properly. So your hairdryer, for example, is 1200 watts, and your computer is 180 watts. Yes, your hairdryer would be more. Why? Because it produces heat. Right? And to produce heat, you need a lot of power, electrical power, to turn a lot of resistance into thermal energy. Whereas with a computer, heat is not the thing you want. Right? Or else it can destroy your computer and all the circuits inside of it. So you don't really want that. So what we're going to do in this question is we're going to test to see if having these two appliances plugged in will exceed our household safety limit of 15 amps. Now there is two ways we can do this, right? Since we know that this is a parallel circuit, we know that the voltage is going to be the same in each one. So they're both going to be drawing 120 volts. And then knowing power, you could figure out, well, whatever you want. Resistance, current, right? And then you can figure out the current here, the total current, total resistance. You can solve the entire circuit. But there's an easier way to do it, right? And that's realizing that since the voltage is the same here, right, and the currents, if you remember Kirchhoff's current law in parallel circuits, the current here plus the current here will give you the current here. So if we're not to exceed 15 amps, what we can do instead is calculate the power that we're not able to exceed. So we have amps and voltage. So power, the maximum power that we can go to would be that potential difference times current, which in this case is 120 volts times 15 amps. And that's going to give us 1800. There we go. Had trouble with my 8 there. Watts. And since current is going to add, so will the power. So that means if I take 1200 watts and add 180 watts, we get a total power usage of 1,380 watts, which is less than the safety limit of 1800 watts. So this is safe to run. And you can do this with anything in your house because most houses will provide 120 volts in Canada to each outlet. And most houses have a safety limit of 15 watts. So if you're looking at one outlet, and you hook up a power cord and you start plugging everything in, you can test to see how much power each thing you plug in is actually taking and whether or not it's actually exceeding the safety limit of 1800 watts. So our third problem sort of extends from our second problem, the way we solved it. It says a student rents a small apartment that has 4 120 volt outlets wide and parallel. She moves in with 6 appliances, a kettle, vacuum cleaner, TV, microwave oven, coffee maker, and a computer. What combination of 4 appliances can she operate simultaneously if the maximum current allowed in the circuit is 15 amps? So same idea, 15 amps with 120 volts means a maximum power outage of this 1,800 watts. So which of these can we add, 4 of them, that is still less than 1,800 watts? A good place to start is, say, the TV and the computer. So we have the TV, which is 100 watts, And the computer, which is 150. I don't really want to hook up the microwave oven because that's not going to go well. I would probably unplug other things if I wanted to use that. Vacuum cleaner, so that's 600. And a coffee maker is the next lowest one, so 800. So there's 4 appliances, and they all add up to 1650 watts, which is under our 1800 watts, so we're safe. We could have also exchanged our coffee maker with our kettle, and that would have been 1750, which is still within the safety zones. We would have been in trouble if we included this microwave oven with 3 other appliances for sure. Okay.